He also lectures in the field of EMC at the Technical Academy and is an officially appointed and sworn EMC expert. He is an author for multiple technical journals, publications, and books. Following the presentation, we'll have a live Q&A with Dr. Zinkner. You can submit questions at any time during the session using the chat box on the right-hand side of your screen. Thank you so much for joining us, and with that, I'll hand it off to Dr. Zinkner for the presentation.
Hello everybody and welcome to the seminar about digital isolators. My name is Heinz and in the next 30 minutes I will tell you about why do we need a digital isolator, what is the basic function of such devices, what are typical applications of digital isolators. I will show you an application which is based on the application note ANSO20, which you may download from our webpage. Then I will show you the typical R&D challenges with this digital isolators. What do you need to consider to have a professional circuit design, and I will show you EMC measurements of this application with some measures which are important for good EMI behavior. So what is the principle of a digital isolator? Let's start first with where is the problem in nowadays in the industrial environment where physical variables like temperature, voltage, pressure, and many more parameters are measured. The problem here is due to the strong electromagnetic fields, overvoltage, transients voltages, which are produced by frequency converters, by magnetics and other electric and electronic circuits. You have high switching currents, inductive loads which generate transient electromagnetic fields, and they all cause capacitive and inductive interference couplings from one to the other cable, high noise on the sensor signals, and ground potential shifts, meaning equalization currents. Yeah? And this electromagnetic phenomena cause malfunctions, interruptions, functional failures. So summarizing this phenomena, the following four requirements arise. We need a safety barrier between the hazardous voltages and the user to interrupt these equalization currents. We need a separation of ground loops between local separated circuits. We need the minimization of common mode disturbances, which occur by a capacitive and inductive coupling from one to the other cable. And in the end, what you need is an interference-free data transmission that all the things work like intended. So the solution is clear. It's not difficult. The solution means galvanic isolation that separates the zones, and they must provide a low parasitic inductive and capacitive coupling. They need a high data rate nowadays from the sensors to the computing devices, and they need a low susceptibility to interference. They must be immune against magnetic field transients and so on. So you may use optocouplers, but they have a low data rate. If the data rate is sufficient, yes, it's a solution. You may use transformers, but in most cases they have a high parasitic capacitance, which again cause common mode noise from between the primary and the secondary side. And in the end, transformers, they should have an impedance matching that you have the bandwidth you need. So one of the new solutions, which I'm going to introduce you to, is the digital isolator. So the digital isolator has primarily a capacitive coupling area between this primary side and the secondary side. You see it here in this figure here, where we have the transmitter and the receiver, everything in a molded compound here, and the capacitive coupling between the primary and the secondary side. So because of the very, very low parasitic capacitance, you see here between 0.5 and 0.7 picofarad, which is the capacitance of the component without PCB, but in the end it can be realized very small. Due to the low capacitance, you need some modulation of the signal to have it in a higher frequency that you can transmit it via the small capacitance between the primary and the secondary side, where in the secondary side it is demodulated, amplified, and then you have your signal back at the output. So this is the basic function of this digital isolator. Yeah, the advantage is the maximum withstanding isolation voltage between primary and secondary here is here shown with 3750 volts RMS, which is a lot. Yeah, you see here there are digital isolators with an integrated DC-DC power supply, which I will introduce you to very soon. And there are the, let's call it the standard devices, which don't have this DC-DC converter on board. Both you can have with a data rate up to 150 megabit per second, which is a lot. Yeah? And they have isolation voltages up to 5000 volt RMS. But be careful. This isolation voltage is, let's say, for transients voltage immunity only. It's not in terms of safety isolation considered. So here again, a block diagram of the digital isolator, but with the integrated DC-DC converter. You see here, you go here inside with the DC-DC, with the DC voltage, and you supply the primary part. Internally, you see it on the next slide in detail, there is the DC-DC converter, which is also isolated one. And the secondary part here is supplied via this isolated DC-DC converter. And additionally, you may use this voltage here or this energy to supply some interfaces, which you, for example, have in your sensor device. You can choose here between 3 and 5 volts, 3.3 and 5.0 volt with this selection pin here. If you put it to the ground, you have here the 3 volt. If you hang this to the VCC, then you will have the 5 volt output voltage. Yeah, let's go to the example of this application, of this digital isolator, an application which has the idea of measuring without ground reference a voltage, for example, in an array of batteries. You can measure between, without any ground reference, the delta voltage via this probe here. Then we go to a level shifter, to a DC to voltage converter. We go to our digital isolator. We buffer the whole signal, and we go out to a unshielded twisted pair cable. At the receiver side, we regenerate the weak and signal, put it again, supply it to the digital isolator. It's AC signal, a digital AC signal. Then we, after the isolation, we go to the frequency DC converter, and we have the output voltage regenerated again according to the input signal. We amplify it, and then we can lead this signal, drive it somewhere to a digital converter and compute it. So here is the schematics of the transmitter. We have here the instrumentation amplifier as the interface, like mentioned in the block diagram. We go to a level shifter because we don't know the polarity here. It can be vice versa. Yeah? It can be plus, minus, minus, plus. It doesn't matter. We shift the whole thing then to a level shifter. We change the voltage to a frequency. So according to the voltage level here, we have a frequency at the output. We go to the digital isolator, isolate the whole interface here, go to the buffer, and via filter and transients protection to our twisted pair cable. This is the isolation voltage here. We need here, if we don't use here an internally supplied the digital isolator, and we need here the voltage to be supplied by a DC-DC isolator. and to have here the galvanic isolation of the power. Here you see an overview of the layer of the PCB here with this barriers here, galvanic barriers. Here again the isolation barrier, here with our power supply here, and here with the digital isolator, so that we have the sufficient barrier of this 3000 volts, which is also considered already at the DC digital isolator here. The schematics of the receiver, we come with our signal frequency, AC signal, to the filter here, which limits the level, has a common mode filter here, and the transient protection go to the differential amplifier, to the digital isolator, which has here an internal DC-DC voltage converter, which is isolated. Then we go to our frequency voltage converter, have the voltage back, go to a buffer amplifier and to the signal out. We can here detect the polarity, because you remember we have shifted it, so we have a range of voltage, but actually we cannot say exactly which polarity it is, because it's between 0 and 8 volt, as we will see later. So we detect here with the signal polarity indicator if it is a positive or negative voltage. And here we have a link which shows, okay, signal indication is here. We have connection to our transmitter. This is again a view of this PCB of this application here with the isolation barrier here. And here it shows you how the whole thing works. So we have an input voltage which may be negative or positive. In terms of negative, it is the green trace here which shows you the output voltage, and in terms of the positive, it's the red one. So between minus 30 and 0, we have here the output voltage between roughly 2 and 5 volts here. And if we have a positive input voltage, we have here an output voltage between 5 and 8 volt. So we can show here by this diodes here by red or green which polarity it is. But sure, if you go to an analog digital converter and to some computing device, it's easy to distinguish which polarity we have. So you regenerate the signal according to the input 1-to-1 and may use it via twisted pair, and it works a length of several hundred meters. Okay, going to the R&D challenges with these digital isolators. You see here at the transmitter, we have external supply in the primary side, and we have also an external supply voltage here at the secondary side. So we need isolated DC-DC converters. At the receiver side, we use the integrated one. So we have here a voltage which is generated, galvanically isolated in the digital isolator already. And in the primary side, we have here, like at the transmitter already, the pi filters and coming from the external supply, which then supplies our digital isolator. You see here something like, it's called here digital signal filter. I will come later to it, what the purpose is for this. Yeah, starting with this already, at the output voltage, you see here the ripple, the output voltage here. It has some ripple like any DC-DC controller has. And the problem in any device, not only the digital isolator here, with this supply voltage, you go to a push-pull here input amplifier here. And at the output, you again go to a push-pull output amplifier, and eventually the voltage you supply here, let's say all the disturbances, all the AC noise you have on the voltage, you will also see at the output. So depending on, let's say, the cleanliness or the noise reduction you want to have in your output signal, accordingly you need a clean DC supply voltage. How is this DC-DC converter in this digital isolator working? We see here, primarily we have 4 channels in this digital isolator here, for example. And these 4 channels are then At the secondary side here, depends what you say, what is primary, what is secondary, but here we assume this is primary, here this is secondary, and on the secondary side, we supply our secondary stage here, what is the receiver of the digital isolator, with our internal signal. The output voltage is regulated through, it's called pulse frequency modulation. So it works a little bit different than a standard DC-DC converter. The frequency and the duty cycle are always the same. But if the voltage is a little bit too high, due to the regulations, let's say circuit here, then the pulses are suppressed. Meaning there are some pulses missing, and if the pulse is missing, the contribution to, let's say, the average voltage is missing, and then it goes down a little bit. So this is the principle here of the regulation mode in this DC-DC converter. Where is the advantage? The advantage is very clear. If you don't change the duty cycle, if you don't change the frequency, you will have a higher efficiency because the duty cycle is always 50%. And you will have a lower EMI noise eventually because you don't have the wideband noise. The frequency is always stable. Yeah, going to the next slide. Here you see one example which is given in the data sheet of the layout, which you should carefully consider. You see here again two capacitors, one at the output, another one at the input, and in the input we have the whole pi filter here, which is shown here. And you see this capacitor here, it's called C in and C out. This capacitor here is very close to the digital isolator. Same the output capacitor, very close to the digital isolator. So it must have a reason. Yeah, the pi filter is, the inductor here is far away, and then we have some millimeters going to the capacitor, which are very close in vicinity of the digital isolator. And you see we have 4 layers here. The second and the third layer are here the same, and the bottom layer is a full ground layer here. On this slide, it can show you very clearly what is it about the distance here of this capacitor. I fixed the DC-DC converter on additional the green PCB here, and put the whole device on this breadboard. And as you can see here, the capacitor here, this buck capacitor has a distance to the digital isolator of about, let's say 8 millimeters. And on this setup here, I put this capacitor already on the green PCB, but still has a distance of about 3 millimeters to the isolator. And the evaluation board, there the capacitors are in very close vicinity to the output and input voltage. And you see here with the distance of roughly 8 to 10 millimeters, we have in the frequency domain, this is the frequency domain between 0 and 700 megahertz, you see up to roughly 500 megahertz, you have a very high noise level. As soon as you go closer with the capacitors to the digital isolator in and outputs, you have a much lower emission level already shown with this pink trace here. And if you go to the evaluation board, which is out, I've shown you one slide before, you have the blue trace here in the frequency domain, and you see there's almost no noise anymore. So the next slide shows you these disturbances in time domain. Again, the capacitors on the breadboard, the capacitors here on the green PCB, and here in very close vicinity on the evaluation board. You see here this far distance, the output signal at pin 6 here, pin 6, the output signal of the digital signal here has a lot of jitter here, and it's very difficult to trigger. So this is not useful for any application. If you go closer with the capacitors, you see here you have already the same signal in time domain like with the evaluation board. So you need to fix these capacitors directly at DC out and DC in here. And then you don't see the difference like in frequency domain and time domain. It is still a difference. You remember on the frequency domain where we have a higher noise, but let's say in time domain it looks quite nice already. But as you can see, we have here a little bit noisy signal, yeah? And this is the reason why we can here add a digital filter at the output here, and this we see on the next slide. Here again, the digital isolator with the internal DC-DC converter, and here is the output signal in yellow here with before the filter, and then we have a digital signal filter with an SMD ferrite, a capacitor here, and there you see the blue trace here. We have reduced the noise level by 50% from 400 millivolt peak to 200 millivolt peak. So there might be applications where it matters if you have a little bit of noise on your digital signal. And this you can reduce very easily by some additional low-pass filter. So going to the EMC measurements, thanks to Sebastian and Patricia, my colleagues in Munich in the EMC lab, who did these measurements here. Here you see our first design of this transmitter and receiver system. Yeah, here the transmitter outside of the chamber, the receiver with the DC-DC converter in the digital isolator. Here on the table with the twisted pair wire here and a battery supply that we can use here the device without the DC, let's say, power supply, which may cause some noise. But you see the EMC result here, the trace between 30 megahertz and 1 gigahertz radiated emission here measured in the chamber and 3 meter distance is quite high. Yeah, what might be the reason? We measured then again the whole device with an additional Y capacitor between the primary and the secondary side. And the emission, as you can see here, reduces a lot. Yeah. We had here 200 we included a 200 picofarad capacitor. You see it here on the figure here, roughly 10 millimeter, 15 millimeters from the digital isolator here, and bridged the isolation barrier with the 200 picofarad. Going to the next slide, you see we changed the position of this Y capacitor, going closer to the IC. We thought, okay, go closer, makes a smaller loop. But the result is getting worse. Here you see very close here to the device. Doesn't help a lot, but it helped to add this capacitor in, let's say, in contrary to without capacitor where we had the higher noise. But what is the solution? Because the noise is still too high. Yeah, we thought, okay, if we distribute the capacitors over the whole isolation barrier, then we need many, but yeah, it's an impractical solution to use such many capacitors. They need a very high rated voltage, and this is not really the good solution. So we changed to a 4-layer PCB. You know, the frequencies on this, the switching frequencies, and there are no digital oscillators and nothing on this thing. They are not very high, but we had the high noise alone by the DC-DC conversion there. And going to the 4-layer PCB, you see the result shows a wonderful spectrum here, no noise anymore. But as you can see here, we used the coupling planes, so the layers, the PCB layers, as the Y capacitor. How did we make this? Yeah, let's look at the layers here at the receiver. You see this is the top layer, the first internal layer, the second, and the bottom layer. And as you can see here, we have some overlapping here. Meaning between this one and this one, you see there is an isolation barrier here, but which is here at the top layer coupled. So here we have a continuous split plane here, which couples capacitively those two together. So you can see on this slide how this works. We have here an overlapping between the top layer, which is in continuous or non-splitted area, and in going in parallel with these two splitted areas, meaning we have a capacitive coupling here between those two areas, then which not simulate but substitute this capacitor, this discrete capacitor we had before, and the overlapping area is then about roughly 300 picofarad and spread it over the whole plane in this area here. The transmitter, it is similar. Here is the 4 layers shown of the transmitter, and you see here again areas which are then coupled together, and shown here is we have here the internal layer 1 and the internal layer 2, where we again have some areas which are isolated and which are coupled together. You see this area and this area, they have coupling here. This is the whole area here which is non-splitted here, and here you have to split the isolation barrier. So you have a capacitance here between the isolation barrier, primary side and secondary side, and overlapping again, which substitutes here this capacitor. Yeah, we can surely assemble an additional capacitor, but the whole thing lives on the distribution here, that we have an, let's say, very low inductive parasitic behavior and spreaded capacitance between the primary and secondary side here. Then you see here we have the combination here of the ground and the ground 2 with the overlapping. We have the isolation barrier area here with the called S ground or shield ground here, where we have the interface here. So the whole thing is isolated here galvanically. And why do we need it? You know why we need it. We reduce the emission, but how does it work? We have the device, transmitter or receiver. We have 2 areas, which we have galvanically isolated from each other. If we connect in that moment, when we connect the peripheral cables, for example, here the battery, and here we go outside from the transmitter to the receiver with the twisted pair cable, we will have some noise because we have a parasitic capacitance between the primary and the secondary side. And with this noise, we have a current flowing, and this might be capacitively coupled to the ground floor, and this may be galvanically coupled if you have a connection to the ground via some AC/DC converter or via some interfaces. But the whole thing has an area. This is a high frequency noise which has an area, loop area here. In this loop area, it radiates then. Gives you the radiation, the high frequency emission, what we have seen before in the chart. And what is the idea? Again, this is the primary side of the digital isolator, secondary side of the digital isolator, or vice versa. And then we have a coupling noise. And we want to close this noise. We want to eliminate this noise. What can we do? We say, okay, if this is the isolation area here with the isolation barrier, what can we do? We can short it by an additional capacitor, that the loop, the noise loop, is inside our device here. And this is what we do with this overlapping of these traces. Then we leave the noise, it's still there, the noise, but it runs inside the PCB and cannot go anymore to the peripheral cables. So we short it by this capacitance, either the distributed via the PCB or discrete, where we would need some more then, and then we don't have this noise anymore on our peripheral cables. And this is how the whole principle works and eliminates the common mode noise radiation of the whole system. That's the end of the presentation, and now I am happy to answer your questions. And thank you for listening, and bye-bye. See you then next time.
All right. Thank you, Dr. Zenkner, for a really educational presentation. I know I learned a lot from that, so thank you. We already have several interesting questions, but I want to let the audience know there is still time to submit your question. Just use that chat box on the right-hand side of your screen. Dr. Zenkner, are you ready to answer some of these questions?
Yes, sure I am. Hello to everybody.
Excellent. So the first one here is asking, is there an application in which a digital isolator is not suitable for?
Yeah, well, where can it be, or should it be not used? Can it be not used? If you have applications where you have to transmit or isolate